Hello everyone, I'm Emir and I'm currently a senior at Robert College High School in Istanbul, Turkey. During the summer, I've worked along with my friends Arda Murat and Emir Çelet with the assistance of Dr. Aydın Özcan on this project called Nanoribbon-based nanoarchitectures as resonant tunneling diodes, which is a hybrid study using IBM's quantum computing platform Qiskit and non-equilibrium green function formalism. So without further ado, let me tell you a little bit more about our project. This presentation will include four main sections: the introduction, followed by thermalization, many-body localization, and state of electrons at graphene nanoribbon edges, then resonant tunneling diode behavior, and then the conclusion. So we had a few main motivations for our research, but perhaps the most prominent one was resonant tunneling diodes, which is a phenomenon where electrons are able to skip through resonant states at specific energy levels. And this can further be characterized by the negative differential resistance, as you can see on the right here. This allows for quick and low power electron transmissions, which increases the efficiency of low power electronics, such as oscillators, frequency dividers, and analog to digital converters, which we use frequently in real life applications. Our next motivation was actually to discover more about graphene nanoribbons, which are 2D allotropes of carbon, and their electronic properties depend highly on their structural and physical parameters. In 2010, Anja Gajm and Konstantin Novoselov actually won a Nobel Prize in Physics for their research regarding graphene nanoribbons. So since then there has been a lot of interest in this topic, and they are divided into two types, which is zigzag graphene nanoribbons, as you can see on the right here, and armchair graphene nanoribbons, as you can see on the left here. And we will further be investigating the thermalization and localization of the edges of graphene nanoribbons, as it is already known that the center of them are already thermalized. So let's talk a little bit more about thermalized versus many-body localized states. So in thermalized systems, the system effectively reaches thermal equilibrium as electrons move freely and they are able to give energy from one another. And thus, there's a loss of information about the initial state as the particle density and the energy becomes uniform. However, in localized systems, we will instead be using localized wave functions as electrons are confined, and thus there's no conduction of electricity, and these will further cause interacting systems to be many-body localized. So to go over shortly from our research, we will first be simulating the edge structures using IBM's Qiskit quantum computer. Then we will use a transition circuit from Ruihao Li, which will break our simulation into time frames and allow us to see each and every one of the time frames and how electron particle density changes, and seeing if it becomes uniform over time, which would lead to thermalization. And then we will be inspecting the Aharonov bone ring suggested by Motohiko Ezawa for a possible resonant tunneling diode. And we will be using non-equilibrium green function formalism to plot the current and voltage curve of this Aharonov bone ring. Now let's move on with the thermalization and many-body localization of graphene nanoribbon edges. In this process, we will be using the tight binding Hamiltonian and adjusting it according to edge effects such as hydrogen passivization, where hydrogen atoms bond with carbon atoms on the edges of graphene nanoribbon as we are cutting graphene. This further causes the electron density to be higher on the edges, which can be observed using scanning tunneling microscopes. Thus, in order to account for this change, we will have to make the on-site potential slightly negative and adjust our tight binding Hamiltonian accordingly. In addition, interactions such as the electron interactions may lead to delocalization, and in order to account for this potential error, we will have to utilize the Hubbard correction term. When we utilize these terms, our final tight binding Hamiltonian will look like the following at the bottom right here. However, in its current state, we cannot use this tight binding Hamiltonian and directly plug it into IBM's Qiskit quantum computing platform. And to be able to do that, we will need to rewrite it in terms of Pauli gates. As you know, our tight binding Hamiltonian is currently in the form of creation and annihilation operators. And these operators can be rewritten in terms of Pauli X gates as The creation operator is 1 over root 2 times the poly x gate plus I times the poly y gate. And the annihilation operator is 1 over root 2 times the poly x gate minus I times the poly y gate. Thus, when we rewrite and reformat our equation, our new Hamiltonian will be like the following at the bottom right here. And then we can plug this Hamiltonian and create a trotterized quantum circuit, which discretizes the time evolution into small steps, so small time frames, which we will be utilizing 9, 12, and 15 qubit circuits. In this case, the poly x gates will be at qubits 0, 4, and 8 to check particle excitations. And we can further calculate the system imbalance using the following formula, where a close to zero system imbalance would show that the edges are thermalized, whereas a non-zero imbalance would lead to many-body localization on graphene nanoribbon's edges. And our quantum circuit, trotterized quantum circuit, will look like the following. And due to space constraints, we actually couldn't show you the 15 qubit circuit. However, it works more or less the same way. And as a result, when we calculate the average imbalances for different values of U and E, which are the disorder strength and the interaction strength, we will find that for our chosen values, which is 1J for U and negative 0.03J for E, we will find that the system is actually thermalized, as you can see on the center here when you look at the given values, and it will be very close to zero, showing that it is thermalized. In addition, if you were to observe the graph on the right, which is about system imbalance versus time for 15 qubits, you would be able to see that the system imbalance converges to zero over time, thus showing that there's a uniform particle density and that our system is thermalized. Now let's move on with the resonant tunneling diode behavior. As previously mentioned, we have proved that the edge structures of graphene nanoribbons are thermalized, and thus we can now search for geometries that yield a negative differential resistance, hence causing an RTD behavior. In this case, we will be inspecting the Aharonov-Bohm ring suggested by Motohiko Ezawa, which you can see on the right, with it being slightly adjusted with ports on the sides to assure current flow. In order to check if our suggested geometry actually provides and works as a resonant tunneling diode, we will need to incorporate non-equilibrium green function formalism, which is used to explore the transportation properties of systems and calculate the response of a system to a constant perturbation. In this case, we will use the retarded Green's function, which can be written as this formula here, where I is the identity matrix and sigma terms refer to the self-energy matrices for source and drain. And we can rewrite it as the advanced Green function like this. In addition, we can use the broadening matrices, which are given below, to utilize them in our Green's function. We can further rewrite the transmission function related to the probability of the transmission of an electron as the following. And in this case, the current flow through the system will be E squared over H times the integral of the following terms. This will further involve a Fermi-Dirac distribution functions, but as these are all very well above high school maths level, we were not able to discover all of them properly. However, we can utilize this non-equilibrium green function formalism in our code snippet and actually use it to calculate the ID curves, like current versus voltage curves, to check if there's a resonant tunneling diode behavior. And you can access our code using the link below. In this case, our current voltage graph will actually provide us with a negative differential resistance, which further proves that the Aharonov-Bohm ring suggested by Motohiko Ezawa works as a resonant tunneling diode. As you can see, the negative differential resistance is between 0.2 volts and 1.2 volts, as the current decreases even though the voltage increases. Now, finally, let's move on with the conclusion. We first used the simulation of edge structures via Qiskit to check if they were thermalized or many-body localized. We added new terms to our Hamiltonian and adjusted it accordingly, propagated the system through time with trotterized quantum circuits, and we saw that there was a close to zero imbalance, which led to uniform particle density, further showing that the edges of graphene nanoribbons are thermalized. Then we inspected the electronic properties of this system using non-equilibrium green function formalism, and we utilized the tight binding Hamiltonian in the second quantizational formalism. And seeing that there was a negative differential resistance right here, we were able to conclude that this indeed proved that a Aharonov Bohm ring was a resonant tunneling diode itself. Thank you for listening to me and have an amazing day. See you soon.